Hi, my name is Mishal Musleh, and I'm going to give a quick demo about our work named RASED. This work was done with my advisor, Professor Mohammed Maqtool. So what is RASED? It's a scalable dashboard to interactively monitor and analyze billions of map updates worldwide. So why do we need RASED? All road network queries, think of routing, range query, and KNN queries like nearest gas station or restaurants within a distance. All these queries mainly depend on the quality of the underlying map. The accurate the map, the accurate the results are. From this, it becomes very important to analyze map data and assess its quality. And there are several studies for this. However, all of these are limited to only very small geographical regions. And why is this? It's because the huge data size and the continuous updates of maps. For example, OpenStreetMaps, which is widely used open source maps, has more than 12 billion map updates since it started and more than 3 terabyte worth of data. This makes practitioners and map analyzers unable to study such amount of data and gain insightful analysis. RASED tackles this scalability challenge and provides the necessary infrastructure needed to assess the map on a global scale, comprehensive and highly interactive analysis for map data anywhere in the world. RASED is available online, and users can use the system to query and visualize various statistics about the map updates, including number and percentage of updates for each country, for each type of roads, comparison between countries, temporal progress of updates over time, availability of metadata, and many other scenarios.
So, how does RASED achieve this? The following figure shows the architecture of RASED, which composes of 4 main modules. I will give a brief explanation for each one of them. The first module is the data collection and processing, which is primarily responsible for 2 tasks. 1. Crawling map updates from multiple sources in OSM every day, and 2. Preparing these updates for consumption by filtering out irrelevant data, merging multiple data sets, and extracting location information, and so on. The prepared data then goes to the second module, which is the storage and indexing, which is a core module in the system. It takes the prepared data and performs offline computations to reduce the response time of RASED and makes it interactive. All map updates are pre-aggregated on several dimensions, such as time and location, road type, and update type. This aggregation process produces around 500,000 new values every day in the form of a data cube. This generates a large number of data cubes, and therefore there is a need for an efficient retrieval of these cubes to make RASED analysis interactive enough for its users. To solve this, RASED organizes this large number of cubes in a hierarchical temporal index structure of 4 temporal levels: daily, weekly, monthly, and yearly levels, as shown in the figure. The lower daily level is the same daily cubes generated by the aggregation. The weekly level includes an aggregation of all 7 cubes that are in the same week, and so on for the monthly and yearly levels. This index makes answering users' analysis queries highly scalable and interactive, regardless of the requested period. It could be as small as a single day or as big as tens of years, and for the whole world. Note that all cubes from all levels have the same number of dimensions and the same size. However, each cube covers a different period. With this large number of cubes at all levels, RASED employs a caching strategy to preload part of these cubes into memory to make queries more interactive. These cubes are selected based on available memory in the system, in addition to few other parameters that are configured for the system, which control the trade-off between the coverage or the total period of cached cubes and the temporal granularity of details in these cubes. The third module is the query execution, which has 2 components: Query Optimizer, which aims to find the best plan to answer a user query while minimizing the number of accessed disk-based data cubes. For example, an analysis query for the period of January 2022 can be answered either from 31 daily cubes, or 4 weekly cubes plus 3 daily ones, or a single monthly cube, and so on. The query optimizer decides on the best plan among these plans. It also takes into account which cubes are cached in memory and which are not. The second component in this module is the query processor itself, which takes the selected plan and load the requested cubes from the index into memory and perform any remaining computations on the fly. The last module is the user interface, which receives user queries and visualizes their results, which we will show in details in the next demonstration. This is the main landing page of RASED, where users can interact through a wide range of scenarios, and we give few examples of them. First is querying. Users can specify the query parameters, which are the temporal range, the type of rows they are interested in, type of map elements, and kind of operation. To the top, users can toggle between absolute numbers and percentage, which is important to realize the amount of updates relative to the network size of each country. Users can also choose to focus on specific regions, such as Europe, Middle East, or the whole world. The country's view will give statistics about map updates for each country. Users have the choice to show it as a table or chart, where the chart has multiple colors indicating different kind of updates. The next scenario is to understand the progress of map updates over time. This is done via the choropleth view, where users can play a time-lapse video that show updates over time. It's worth noting that users can use these views as additional parameters. For example, users can select a country from the country's view, and all other views will reflect the statistics for the selected country. The fourth scenario is to understand map update activity for each type of road, and it can be shown as a table or as a chart. For example, for the country that is selected here, which is the United States, we can see that the service roads are by far the most updated ones. The next scenario is to compare between multiple countries to see their map update activity over the requested period. Users can select more than one country from the country's view to have their update activity drawn together in the time series view. Users can continue to add or remove other countries, or to zoom in or zoom out in the time series view to inspect the values at different points in the timeline. Next, I'll change my focus again to the United States and move to the next scenario, which is about inspecting a sample of map updates according to all query parameters and all filters that are selected from all other views. As we can see here, this is a sample of the updates with their locations drawn on the map. If we click on any of those pins, we will be redirected to inspect the exact updates. So we can see here what was created and what was modified during that update. The last scenario is about inspecting the completeness of map metadata that are annotated with roads. For example, the maximum speeds or the number of lanes. This is done through the metadata view, which gives us a table of all available metadata with their coverage, which is the percentage of roads that have a value set for this metadata. Note that we can also change our filters, such as the type of roads that we are looking for example primary roads here, to check the coverage against only those type of roads. For example, 50% of primary roads in US are missing the maximum speed metadata. I invite you to visit the dashboard, and I guarantee you that you will enjoy exploring and analyzing map updates worldwide. It's available online at www.rased.cs.umn.edu. And with that, I conclude my presentation, and thank you very much.